Okay, it's starting. All right, welcome back. Thank you for attending. I guess new faces here, and then probably some old faces on Zoom or YouTube, just depending on how this gets watched. I know a lot of people are on vacation right now, so hopefully you can see everything. Rebecca, if there's ever anything that you can't see on Zoom, please let me know and I'll adjust the video setup.
Sounds good.
So for the first three lectures, we've kind of talked about some examples of varieties in algebraic geometry. We've talked through the first few subsections of Hartshorne and a decent amount of Joe Harris's book, A First Course in Algebraic Geometry. So the key things to remember are regular functions and regular maps. And as those show up throughout this lecture, I'll just kind of remind us what those are as they're relevant to what we're doing today. But as you can see, initially we'll be talking about some commutative algebra topics like the Nullstellensatz, and then we'll move on to starting to talk about Sheaves, and we'll give that motivation later. So many algebra geometric constructions have come out of geometry classically, but a lot of things came out of commutative algebra initially. And so I think I would be remiss if I didn't talk about some of that commutative algebra as it pertains to motivating schemes, and there's a particular correspondence that we'll consider. So when we think about affine varieties, which so far we've mainly talked about projective varieties, when we think about affine varieties, like things living in something that looks like this, we want to be able to relate these things over somehow to ideals. And this is kind of going to be our theme for today, is how do we make this relationship a bijective correspondence? And this was done kind of first by enlarging this side of things, by looking at like a larger class of ideals that makes this a bijection. And this is what we'll talk about with the Nullstellensatz. But then the other way to talk about this is by enlarging this left-hand side. And this is where we'll talk about sheaves and then eventually schemes. So for now, we'll consider the following. So given a variety, V, we will define the ideal of V to be the set of functions k over x1 to xn, where k is some algebraically closed field, such that f of p is equal to 0 for all p in the variety. So these are points in the variety. And so this is kind of all of the functions which vanish on the points in the variety. Likewise, given an ideal J, define the vanishing of this ideal to be the set of points P and K such that f of P is equal to 0 for all f in the ideal J. And so this is, we'll call the ideal of a variety.
Unless you mean to only do one-dimensional things, yeah.
Yeah, KN. Yes, okay. But with that amendment, these are valid definitions. We have the ideal of a variety, and then we have the vanishing of an ideal. And we would kind of love for this, for an idea to be true that if we, take the vanishing of an ideal, and then we take the ideal of that vanishing set, we should maybe get back the same ideal. Or that if we take, some ideal, we take its vanishing, we take the ideal, we take the vanishing, we get the same thing back. But it turns out that this isn't true. So like we would want it to be that, for every j, we have, I j is equal to j. But there's a simple example that we can use to kind of cut this out. So pick the ideal x squared as j. And with this, we can take, well, the vanishing of j, it's going to be the singleton set 0. And so then the ideal of 0 is most naturally cut out by the ideal of x. And so we kind of see that, in fact, this is not a true statement, and we don't have this nice relationship. And this kind of is where we first see this idea that the correspondence that I presented at the start of this is not, in fact, bijective. And so, in general, we're going to define something that's kind of going to solve this problem. We're going to define the radical ideal. I have to let Jackson in. All right. Okay, so we'll go ahead. We will define the radical ideal to be, well, for some ideal j, square root of j is the standard notation, but it's the set of f, k, x1 to xn, such that f to the n is in j for some. And so here, this is where we get out Hilbert's Nullstellensatz. This is kind of our sense of enlarging the right-hand side of that correspondence, enlarging items. Hilbert. Nullstellensatz. That for any ideal j k over x1 to xn, then we have I j is exactly equal to the radical ideal of j. And so, yeah, we'll go through a proof of this, but for now, I think just to show that this is really what we're looking for intuitionally, right? If we had picked, j equals x squared, we saw that I bj is x, and it's certainly x to the second power is in j. Okay. So here's a proof of the Nullstellensatz. So take our setup as is. We want to first show one set inclusion and then show another set inclusion. One side is easier than another. So we pick f in the radical ideal of j. Then we know that there exists an m with f to the m being in j for some m greater than 1, greater than or equal to 1. And so then for all a in the vanishing of j, we have that f a to the m is equal to 0. But then we know that this polynomial ring we're working in is certainly an integral domain, and so we have that f of a is equal to 0. And so f is in the ideal, the vanishing of j. So this is kind of our first direction done. And marking this as such, we have that within A, J. Okay, and now the next part is a bit more complicated. So direction 2. Now, take a function f in I Vj. And we're going to consider the ideal, and this is kind of just a trick, and we'll talk about why the trick works later in the proof. But consider the ideal, I'm going to use a capital K. Let's see. We'll consider a capital K, and this will be the ideal cut out by the generators of J, and 1 minus YF. And this is going to be in the ring K, x1 to xn, and then we're going to add this y. And to make this seem like less of just an arbitrary choice, what we're going to end up doing is we're going to make a choice of what y is, and it's going to be a localization by some function. And so based on that localization, we're going to show some things that prove it through. Okay, so we're going to assume for contradiction that K is in fact the whole ring. And what we really want to show is that K is proper.
Other way around.
Oh wait, other way. Oh wait, sorry, yes. Assume that this is a proper containment. Thank you. Yeah, we're going to assume that K is proper so that we can show that it is the whole ring, and then we can do our localization trick. So then if K is proper, then there exists maximal ideal M. I'm just going to call this ring capital R for now. I don't think I use that notation anywhere else, but just to save some headache. Okay, so there exists this M in R, which is the maximal ideal, such that K is contained in M. They might be equal, they might not be, we don't know. Well, we know that since M is maximal, and since K is algebraically closed, that R mod M is a finite algebraic extension of K that happens to be K. And so, because of this fact, there exists A1.
You mean K mod M? Or R isn't, M isn't in R. R is an M.
R is the polynomial ring x1 through xn with y.
Oh,
Add maximal ideal of this guy.
you have your inclusion backwards. R has to be contained in a maximal ideal, not contains a maximal ideal.
K is contained in some maximal ideal.
You have it backwards.
I do have it backwards.
And previous, there exists M contained in R backwards.
Good catch. All right, is all well up to here?
Wait, now R mod M doesn't make sense. I think you need K adjoin x1 through xn and y mod M. The whole ring mod M is K. No, but R is contained in M, so R mod M doesn't make sense.
I think, hold on, let me rewrite this line.
Okay.
Let me do it without R. It's going to save less space, but I think it will be more clear. Okay, so we have K assumed to be a proper containment of this polynomial ring. we have that, okay, K is contained in some maximal ideal. And note that this is K, this ideal, not K, the coefficient field. And then what we're going to have is that the quotient K x1 to xn comma y mod m is K by Zariski's lemma. And this is what it is meant to be this whole time. Okay, so this is acceptable. Okay, then by this, there exist a1 through an, and then just a b in K, such that m is generated by x1 minus a1 through xn minus an, and then y minus b. And so then, because J is contained in M, the point A, which we'll define to be the coordinates A1, AN in an affine space. I guess this is really KN. This is really going to also be A's in the vanishing of J. Okay, and so since F is in the ideal of the vanishing of J, we have that F of A is equal to 0. Okay. But then we also have this property that 1 minus yf is also in the maximal ideal. And so evaluating this at AB, at y, so let y equals b, and f evaluated at A, well, this is 0. And so we end up getting that 1 equals 0, which is a contradiction of our assumption. Well, this is just a contradiction, actually. And so we end up getting that this is not a proper containment, but rather, this is a set inequality. All right. Is everybody clear up to here? Okay, so now we're going to do our little localization trick. Okay, so since this is true, then we know that there exist G1 through GR, H, and Q1 through QR, J, such that 1 is equal to G1, Q1, plus dot 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 dot, plus GR, QR, and then plus H times 1 minus YF, simply as this is an element of the ideal J. And now here's where we're going to do our nice little trick. So we're going to pick y equal to 1 over f, so that k, capital K, no, so that ordinary K, well, I guess both, really, yeah, capital K, is really equal to the localization of this at f. And so then this is equivalent to saying that 1 is in the multiplicative set j, k, x1, or xn localized to f. Taking this equation, since we had picked the GR to be arbitrary, and clearing denominators, what this means is that there exists capital N such that f, the capital N, is in J, and this means that f is in radical ideal J. And so we've proved our statement. Okay, so this is Hilbert's Nullstellensatz. This is like one of the huge classical theorems in algebraic geometry and commutative algebra. Are there any questions kind of about this proof so far? Okay. So there's one specific thing I kind of want to note because it's going to show up a decent amount in scheme theory, which is that of nilpotent elements and the nil radical, which is a special type of radical ideal. So, so we consider the radical ideal of the zero ideal, and this is in some ring, or in general something that just looks like a ring. So this is the ring of elements who have some power equal to 0, right? And so sometimes in scheme theory we'll write this as eta of x, where x is like a ring. And what this is again, a x such that a is 0 or something. Our particular interest in the no radical comes from taking the no radical of maybe a coordinate ring or something that we think is the coordinate ring of a variety. And so just kind of as a reminder or as a definition for people who weren't here for the first few lectures, the coordinate ring of a variety x is defined as a of x. It is a polynomial ring mod the ideals of the curves that generate it. I guess really not that. F1, Fs. And so this is what we call the coordinate ring. And so what this really is this is a K algebra. And so what we're kind of interested in is if we have some finitely generated K algebra, and we want to know whether or not this is the coordinate ring of some variety, well, we would maybe like some conditions on this no radical thing to tell us whether or not this is or is not the case. And it turns out it can do that. So given so corollary, given a K algebra A, A is equal to A of x if and only if the no radical of A is empty, and then also A is finally generated. And we'll see this next lecture kind of mirrored in our scheme theory side of things. We'll talk about this when we classify schemes. But yeah, this is just something to keep in mind as something that can show up again and will show up again. Okay. This is really funny. Rebecca, you know how Zoom was acting weird yesterday? It's been acting weird all day. It's been giving me pop-ups. And now it's popping up in the middle of the lecture saying I need to sign in now, otherwise it may lock me out. Anyway. Okay, so now I want to go back and talk about this correspondence that I brought up at the start of the lecture and give some motivation for schemes. So, right. The correspondence that I'm talking of is that of subvarieties and affine subvarieties and ideals of K x1 for xn. So what we said we really want is for this to have a bijective correspondence, right? And we did this one way where we were able to realize affine subvarieties as having a correspondence to radical ideals. But now, maybe what we want to do is we want to enlarge this side of things. We want to enlarge our notion of subvarieties to schemes. So the way we're going to do this is, and actually, hold on. Let me just make sure that there's a paragraph in here that I want to read because Harris did just really a great job of talking through this. Yeah. So I guess, naively we'll call an affine scheme just something that has a correspondence to ideals of this type. And so, for example, if x is in AN, is a variety with some ideal I equals I of x, we'll define a function on x to be an element of the coordinate ring, and we'll define the intersection of two such varieties as the joint of the ideals. The data of a map between two such varieties, x, y, are equivalent to the data of a map between their coordinate rings, and so on. And so the point is really that all of these things make sense whether or not I is a radical ideal. And so the scheme associated to an arbitrary ideal I may not seem like a geometric object. It's an algebraic object, namely, especially in the case where I is not radical. But it does behave formally like a geometric object, and it encodes extra information through the no radicals of interest. And so our naive notion of what we're trying to do with schemes is we're trying to explore that. And we're trying to maybe exploit some of those structures that are there in the algebra that are not there in the geometry explicitly. So there's a way of doing the same thing for projective varieties that's in the notes and is typed up. But since I'm at the halfway mark and this is kind of a two-part lecture, I'm going to switch over to that. So if you're interested in the scheme theoretic case of cutting out a variety projectively, feel free to take a look at the notes or ask me about it after. But either way, it'll work out pretty well. Okay, so answer 1, radical ideals assigned to varieties. Answer 2, schemes. Okay, so this is just kind of like a managerial note about where we're going with this seminar and kind of how we think we're going to take this. We started by following a classical algebraic geometry book, Joe Harris's book, his first course. That book is wonderful because it has so many examples, and it's really great. You get really great geometric intuition. I want to steer this in a specific direction to answer certain questions by the end of this course. And I think that there's a pretty clear way to do that. So what we're going to do is for the next few lectures, by few I mean 6, we're going to discuss machinery, and then in kind of the 6 after that, we're going to be building up to a bunch of big payoff theorems. And so we'll answer some enumerative questions. I gave a seminar talk a few months ago, and I'm basically going to recreate that talk at some point. That's cool. It's enumerative questions about intersections of varieties with linear subspaces. We'll talk about lines on hypersurfaces. So one of the big theorems is that the cubic surface contains 27 lines. So that's something we'll prove in the last lecture of this series, hopefully. And along the way, we'll talk about a bunch of stuff. We'll talk about sheaf cohomology, check cohomology, de Rham cohomology, and kind of how those interplay, and then Chow rings of varieties and algebraic cycles. So it's just kind of like a way of pushing stuff through. But to do that, we need schemes, and so we're going to talk about schemes for like 6 lectures. Okay, so to talk about schemes, we need sheaves, and hopefully by the end of today's lecture, it'll be somewhat clear why. So as an introductory example, give Rn the Euclidean topology, and then we'll define C infinity on R to be the sheaf of smooth functions on all open subsets of Rn. Convention, I use this little subset with a bubble on top to mean an open subset. This is more useful than saying that there's some topology tau on Rn and that this is an element of this topology. I like this is better. Okay, so we're going to just kind of notice some things that we get about smooth functions defined on open subsets of Rn, and we're going to try and piece together what our intuition for a sheaf should be. So we're going to denote this math cal O of U as, I guess, sorry, yeah, this is going to be a set, this is going to be a sheaf. So this is going to be pairs of functions and the subsets that they're defined on, where UI is an open cover of U, and then satisfying something that we're going to talk about and kind of self-derive. So we'll notice 4 key things. The first is that if we have an inclusion U into V, then we have a natural restriction from V into U along the section OV to O. And precisely what this is doing is we're saying that, well, if you have a smooth function on a large open set, and then you shrink that open set, that same function is still smooth on that smaller open set. So this is a natural restriction. Okay, the second thing we're going to notice is that if we have a string of inclusions, U into V into W, it doesn't matter what order we restrict in. We can pass back down W to U, or we can go W to V to U, but it's all going to commute. And so really what we're saying here is that res W to V these all commute. So res W to U, and then res V. Right, it commutes. And this is the same logic. If you have a large set, a medium set, and a small set, and you have a smooth function on the large set, it's also smooth on the medium set, and then it's also smooth on the small set, and it doesn't matter what order we restrict in, as long as we maybe don't try to move back up. Actually, I guess that doesn't really even matter in this case. Okay, and so then the other 2 things that we're going to notice is that I'm going to call them specific things. So this is called the identity axiom. So given F1 and F2 smooth functions on a subset U, and some open cover UI for some indexing set I on U, and if we further stipulate that F1 restricted to UI is equal to F2 restricted to UI for all I, then what we have is exactly that F1 is equal to F2. So basically, we can identify functions on open sets by looking at like small coverings of open sets. And so this is kind of our first notion that a sheaf is really telling us how local and global data talk to each other. And that really that's like what we're looking for out of a sheaf. Another way of thinking of this is like there's at most one way to glue together pieces of functions on small open sets, right? Okay, so our second idea is going to be gluability. So if we take sections Fi in O of Ui for all I, such that Fi restricted to Ui cap Uj is equal to Fj restricted to Ui cap J, basically functions that agree on intersections, then there exists a function f in the global section O of U such that the restriction from U to Ui of f is exactly equal to Fi for all I. So I think really the best way to think of this is saying there's at most one way to glue. And this is at least one way to glue. And our big theme for Sheaves is going to be we want local data to tell us about global data, and we want global data to decide things about local data. And in fact, this example, you'll notice we've used literally nothing about the condition about smooth functions, except for to illustrate a few examples. And so what we're going to kind of conclude is that really this could work for continuous functions, real analytic functions, or just plain valued real functions. And we can make such a sheaf out of these functions, provided we stipulate the right things. Give me a set, we can sheafify it. Again, I've said all of this without really saying what a sheaf is, but suffice it to say that this gets it done. One more thing before we move on to this formal definition is we're going to define something called a germ and then a stalk of a sheaf. So there's kind of like a farming analogy of sheaves going on. Like if you have like a sheaf of wheat, well, each item of wheat is typically called a stalk. And then like the germs are like the things living at the top of the stalk. And so there's something of a geometric analogy going on here. Okay, so I kind of boxed myself in awkwardly here, but I'm going to define germs here. Okay, so we're going to say that the germ of a smooth function f in O of U at a point P we want to think of it as like the shred of a function by that point, because we want in some small neighborhood around P, we want functions to be determined by their local behavior around P. This is what we mean by germs and stalks. And so germs, so a germ is an object of the form f comma u such that P is in U, F is in O of U, and then modulo the relation that F comma U is identified with G comma V if there exists W contained in U and V such that F restricted to the smaller set W is equal to G restricted to W, and P is like that. Okay, I think it's time for an illustrative picture. So given our point P, given some large open set U, and then we're going to take these sets, smaller U and smaller V. Maybe we'll call them like U1 and U2, just for the sake of it. U1 and U2. I know it's bad practice to switch notation in the middle of the example. My apologies. What we can do is we can kind of say, well, given some function defined on U1, maybe this orange function, that's defined at P, maybe it looks like this. We'll call this F, and we'll call this intersection W, right? So W lives here. Maybe I'll do that in white, actually. And then if we take some other function g that's also defined on these two open subsets, well, g can do whatever it wants out here. And it can do whatever it wants in U1 as well. But in this tighter neighborhood around P, it has to mirror it exactly, right? If we're identifying them together, right? And otherwise, a different equivalence class of functions could just do something like this, and we wouldn't identify the yellow one with the blue and the orange. Is this clear for Teams people? Can you all see this? Okay. And so the intuition of what germs do is they tell us, well, in the smallest possible neighborhood for each specific function with respect to other functions, we want to be able to match up functions in terms of their local behavior, and we want to determine it exactly around this point P. Okay, so we call the set of germs at P the stock of P, and then we're going to make a choice of notation that's mirrored by some other things that we've talked about, and we're going to say that the stock at P is this thing that's going to be O, P, and this is going to be a set of groups at P. This is in fact a local ring. I'm not going to go into that too much just for the sake of time, but if you know what a local ring is, this is one. It's not terribly hard to verify. Okay, so now we're going to give the formal definition of a sheaf. We're going to give some examples of sheaves, and then we're going to talk about properties of sheaves and morphisms between them. So the formal definition starts with a pre-sheaf, and what a pre-sheaf is you're given a topological space. A pre-sheaf on that topological space says that for each open subset, you can define this section, which is like O of V or O of U. And that for each O of V and O of U, where you have this inclusion, there exists a restriction map that behaves nicely, the way that we defined it already. And then we also need that if you restrict U to U, that's the identity. From this point, though, this is a pre-sheaf, right? So just by saying you have a topological space, you have open subsets on this space, and then you have the existence of restriction maps that adhere to this condition that if you restrict a subset to itself, it's the identity map on that section. This is a pre-sheaf. All a sheaf is a pre-sheaf with the sheaf axioms. And if John is watching this, he'll have a little chuckle here, because he's been making that joke all summer. But yeah, okay, so a sheaf is a pre-sheaf satisfying the sheaf axioms, and what I mean by that is identity and gluability. And nothing about these definitions changes, right? You have at most one way to glue things, and you have at least one way to glue things. So you have exactly one way to glue things in each section for any open cover that you pick. Okay, so this is great. We have kind of the intuition of what a sheaf is, what you can put a sheaf on, and how we're going to use this, right? We want to take functions on a topological space. We want to glue them together in such a way that global and local data communicate with each other nicely. That's what we wanted of this. Now we'll give some examples of these. Okay. Any questions, just kind of while I'm erasing? Cool. Okay, so our first example of a sheaf is going to actually just be the restriction of a sheaf. So let F be a sheaf on X. This is kind of the typical notation for F being a sheaf on X. So if we have our sheaf on X, and we pick U to be open in whatever topology is on X, then we can define the restriction sheaf Fu, which is the set of sections restricted to U of V such that, which is, I guess this is actually just F of V. This is a set of F of V such that V is an open set. So this is a natural thing. This is called the restriction sheaf. This is in some ways can be viewed as an extension of what's the name of the topology? Perish the thought. If it comes to me, I'll say it later. This is an extension of something from topology that I can't remember the name of. Okay, the skyscraper sheaf is another simple one.
Do you mean a vector bundle? Do you mean a vector bundle?
I do not mean a vector bundle. Although I can see where you're drawing that intuition from. I mean like a literal topology, like point set stuff. Whatever. It's fine. I'll add it to the errata in the comments. So the skyscraper sheaf. This is just kind of a classic example. So if X is a topological space, if we pick some point P in that space and S any set, then we can define the inclusion map from the set containing P into X. This is continuous if you endow this singleton set with a discrete topology. Then we can define this as sending, I guess the image of this is for any set of things, I guess little s in S, big S. If U is defined as S, if P is in this open subset, and it's defined as the singleton set of little s, if P is not. And so this is called the skyscraper sheaf supported at P, and this is nice. You can work out that maybe this is a good exercise to work out if you're interested in this sort of thing, that this is in fact a sheaf, but it's somewhat tedious for what we're doing here. The really important example of a sheaf that we're going to talk about pretty much from now on when we say sheaf is called the structure sheaf. So the structure sheaf is, if we take, let X be a ring, and let O of X be a sheaf whose elements are from the ring, with elements from the ring. So sections over open sets are called functions. So F is called a function. And then just on the entire set, right? So O of X itself, X, functions are called regular functions. So in the context of what we've talked about so far with varieties, regular functions, and rather the ring of regular functions, was this big deal, because what we wanted to have was given the Zariski topology on a variety, we wanted to be able to say that if you had a variety x, you could say that O of x, or Ox of x, was the set of functions f in your polynomial ring such that there exist functions g and h, so that f was the quotient of g and h on u, and h was not. And so you could view this as like a localization around 0, and for h. And so this was like one of the big build-up things from the first few lectures. If you're interested in this, or you haven't seen this before, feel free to take a look or ask me after. And that basically, if we can get subsections of this, we get functions defined on sub-varieties of a variety. Now, in practice, when we talk about schemes, x is going to be something different. So this notation is somewhat, it's not quite the same. And this will be obvious next lecture. But yeah, so this is the structure sheaf. Yeah, it's just hard to get into that without talking about the Zariski topology on schemes. So okay, this is really going to be a next lecture topic. Okay, so I do want to talk about exactly two things before we finish off in about 5 minutes. So naturally, there need to be two somewhat light things. For people who have done enough math to do algebraic geometry, you can probably surmise that there are maps between sheaves, and so then in some way sheaves form a category. So morphisms, sheaves, if you have f and g are sheaves on x, then you can have maps phi from f to g. And what these morphisms need to satisfy is they need to satisfy restriction. So basically, we need to send sections to sections. So phi should be sending phi of u goes from f, u, the section over u, the section over u and g. And this should, adhere to further restrictions. So namely, the triple stack commutative diagram that we talked about earlier that naturally commutes should still naturally commute through this morphism, but that otherwise this is kind of what we're expecting out of this. My strong example requires the structure sheaf. So what I'll say for now is that morphisms of structure sheaves are regular maps. And I will start probably the next lecture by explaining that further, because there are some things that I just needed to define for that to be clear. Okay, the final thing that I want to discuss is properties determined by stalks. So there are really two ways to think about sheaves, and one is in terms of open sets, which is certainly the categorically correct way to talk about them, but it's maybe not the easiest way to think about sheaves. The easier way to think about sheaves is in terms of stalks and germs, and in terms of how local data forces global data. So I'm going to state some results that I've proved in the notes. If you would like a thorough, rigorous proof, please look in the notes. Or feel free to work out. Either is going to do you well. So there's kind of a lemma that morphisms of pre-sheaves and morphisms of sheaves morphisms of sheaves induce morphisms of stalks. And so the idea is exactly this. In the same way that we have to respect the gluing restrictions on subsets and their covers, sending sections to sections, on each section, for each point, we should be able to send stalks to stalks and local rings to local rings. And so this is exactly kind of what we're going for, is local data is preserved by morphisms. And then furthermore, sections, this is a legitimate theorem, sections are determined by germs. And so what I mean by this is that the map from a section to the product over all points in this open subset of stalks is an injection, right? And so sections are determined by germs. Okay. Finally, the main theorem that I'm building up to here is that morphisms of sheaves are determined by stalks, not just morphisms of stalks, right? So morphisms of sheaves induce morphisms of stalks, but then morphisms of sheaves are determined by stalks. And so instead of stating this formally, I'm going to kind of wax through the geometry here. I'm going to say that what we really want is, if we want to relate two geometric structures, or two varieties, or two schemes, we want them to be related entirely by local data, which is determined by stalks. And so in the same way that the sheaf and the structure sheaf related to a scheme or a variety are determined exactly by their local data, we want that to carry over to relationships between varieties and between schemes. And so the purpose of sheaves, if you take nothing else away from this lecture, the big takeaway is that sheaves are here to make it so that we have exactly one choice about how to glue things determined by local data on a topological space, and that local data should communicate with global data, and that local data should actually determine global data. And it should determine the relationships between the global data of two different geometric objects. Okay. That's all I've prepared. Thank you. Okay, any questions before I stop the recording? Okay. Stopping the recording.